Okay, good morning class. You're on to Mambo with Jarvis, and this morning we'll be looking at arithmetic, the aspect of mathematics that pertains to arithmetic, and the topic under consideration is logarithm, and this is for grade 10. I even indicate that there. This is for grade 10, but the way my videos are structured is such that anybody at all, irrespective of your grade, you can watch and understand what I'm saying. I try as much as possible to be very, very simple in my explanations and narrations. Okay, so what is logarithm? Let's start by trying to give ourselves a conventional definition of what we were told logarithm should be. So the log of a number, it applies to a number, the log or the logarithm, log for short, of a number is the power by which a base is raised. The log of a number is the power by which a base is raised. So what does that mean? If I imagine a number n, it means that the logarithm of this number will be n equal to, let me take another base, take a base a raised to the power of b. B in this arrangement is the logarithm. A in this arrangement is the base, and n in this arrangement is the number. But watch carefully. This number here is what we call the anti-log or anti-logarithm. Don't worry, we'll come to stretch the ideas later. So the log of a number is the power. The log of a number n is the power by which a base is raised. So another word for logarithm is indices. Shocking. When we talk about an index, now look at this, because students find it difficult to believe that these things are related. Index, logarithm, superscript, power, all mean the same in the context of logarithm. So when we talk about index, logarithm, superscript, power, all mean the same thing. And that's the first thing you need to understand if you're to bring the concept of indices to logarithm. But that's not my approach today. I'm just trying to help you see that these things exist. In subsequent classes or in a different class entirely, I will build in this line. But take note that index, logarithm, superscript, and power are one and the same thing. So our textbook of reference today would be, I'm using two books simultaneously, I'll be using Essential Mathematics, and I'll also be using New General Mathematics. I'll let you know when I'm taking examples or problems from each of the textbook as I go. This is not my approach for taking on this class, because if I go with this approach, I'll hit something else. In your grade 8, GSS 2, you were taught something. There's a topic you learned called standard form and indices. Those topics were supposed to set up logarithm for you, just like what the Marvel Cinematic Universe they do. You have a little franchise that sets up a bigger thing to come. So indices and indices and standard form was supposed to prepare us for logarithm. And that is the approach I want to take in looking at this topic. So what's the main requirement for studying logarithm? Your standard form must be standard. So without wasting time, we're going to try hands on standard form, and we'll go to our New General Mathematics. If you go to page 19 of your New General Mathematics, exercise 1G, oral or written test, You're going to see some questions there, and if we can write out the standard form for all of these numbers, then we are ready for logarithm. Okay, on the board is written for us exercise 1G. Like I said earlier, the model of this, my approach or my model is to ensure that you have no issue with your standard form. And we have 20 questions on the board to write in standard form, because you're going to see how beautiful we're going to use these questions to move to what? To logarithm. Now, you have 20 questions on the board, and by standard practice, you should be able to clear them into standard form in 5 minutes. 5 minutes is the maximum time you should be able to clear this into. I know for starters it might take you longer than, but the ideal thing is to clear this out in 5 minutes. So how do you achieve that? Look at this. The concept of standard form is the expression of, I've done a lot of videos on this, and I'm trusting you may want to go to my YouTube channel to check these videos out. The concept of a standard form is the expression of a decimal fraction as a unit decimal multiplied by 10 raised to the power of what? Movements. Well, that's storyland. We can do that practically on the board, and then the definition becomes very, very real to you. Now look at this. If you look at the first question, this is a unit decimal. A unit decimal is a decimal such that the highest occurring number, the highest occurring digit is a unit. So for this, we have nothing to do here. We are not making any movement. So it's simply the word 4.35 times 10 raised to the power of what? 0. And that takes care of that one. For the next one, we will write it as 7.88 times. What is the movement we have made? Now, to restore this, this is a small number that we are trying to make big. When you try to make something small to become big, what you have done is that you have brought into big something that should not, and as such this becomes a negative movement. So we say that if you move the decimal place to the right, what you have is a negative what? Movement. Alright, for this we just start by writing 1.903. So you must know what a unit decimal is. 1.903 times, what's the movement? We come to this point, 1, 2, 3, 4, 5, 6. And that will be 6 movements. When you move to your left, you are making positive movements. When you move to your right, you are making what? Negative movements. So that settles that. This will be what? 6.313 times 10 raised to the power of what? We start from here. What did I do to get 6.3? 1, 2, 3. 3 negative what? Movements. Now, this is a tricky one. 6.7. The big question here is 0 significant? No. So the tens in this setup is what? Not significant. So we can write this as what? 6.7 times 10 raised to the power of 0. There was no movement because this is also a unit decimal. If you've seen my videos on arithmetic, you understand this very well. We can form numbers by combining any digit. So 0.6 technically is actually what? 6. Because the tens is not what? Significant to what? To us. So this is what? 6.7 times what? I start here, I go back. This is what? 6.7 times what? 10 raised to the power of what? I start here. For every whole number, you start at the digit ending the whole number. That's where the decimal point will be. So you count 1, 2, 3, 4. For this, it will be what? 1, 2, 3, 4. So that will be 6.7 times 10 raised to the power of negative 4. This is where the decimal point. For decimals of smaller magnitude, you start from left to right. Alright, therefore this it will be what? 4.8 times 10 raised to the power of 4. Movements 1, 2, 3, 4, 5. The whole idea here, if you've seen me take this course in grade 8, the driving thought is this. You're trying to make a small number to become what? Big. And the only way you can balance that out is to make this one a negative, right? Now this is a big number, so we expect to have a positive. 1.202 times 10 raised to the power of what? 6. 1, 2, 3, 4, 5, 6. This will be 3.5 times 10 raised to the power of 0. No movement is made here. This will be 3.5 times 10 raised to the power of, starting from my right to my left, 1, 2. This will be what? 9.97 times 10 raised to the power of what? 1. Negative movement from left to my right. This will be what? 5.512. So the technique here is to write out the standard, write out the unit decimal and decide the number of movements you have made to get that one right. And this will be what? 1, 2, 3, 4. We're done with this, so we come to this now. This will be what? 9 times 10 raised to the power of what? 0. This will be 9 times 10 raised to the power of 1, 2, negative 2. This will be what? 7.64 times 1, 2, 3. 10 raised to the power of what? Negative 3. This will be what? 4.345 times what? 1, 1, 2, 3. 10 raised to the power of negative 3. This will be what? Oh, positive 3, sorry about that. Then this will be what? 3.07 times 10 raised to the power of what? 2. And this will be what? 1, 2, 3, 4, 5, 6, 7. 4.05 times 10 raised to the power of what? 1, 2, 3, 4, 5, 6, 7. Negative 7. So we have cleared the standard form. There are other technical things we're supposed to talk about, but I'm not doing that in this class. And so from this, we will now go into the use of tables to solve problems. Remember I said that if you can handle your standard form, you have solved up to 80% of the problem. So we're going to now go from here straight to use tables to solve problems involving logarithm. Okay, so we are back to the next phase of our work, which will involve use of logarithm tables to solve problems. There's something we call mathematical tables, and if you have one, you discover that there is a table there called logarithm, and there's a table there called what? Anti-logarithm table. So these are the tables you need to handle problems in logarithm. The logarithm table and the anti-logarithm table. What most writers of modern math textbooks have done is to place this textbook, tables behind the textbook. For instance, if you're using the new general mathematics for SS1 or grade 10, if you go to the back of the book, and you check page, if you check page 251 and page 252, you're going to see in 251 what is called logarithm of numbers, and in page 252 is called the anti-logarithm of what? Numbers. Alright, so these are the two tables you would need to attend to any problem relating to what? Logarithm. Okay, but for now, to drive home our point, we'll be looking at exercise 1J, and that's found on page 24 of the new general mathematics textbook, page 24. We'll be using that to we're solving problems from that exercise, and we'll see how we can work out problems using this new idea. Now, I usually use this approach, my 3-column approach. Some writers will use 2, but you will soon understand why I am using this. For me, it makes my work very neat. I always like to solve problems and mentally do everything without having to struggle. So having used this over the years, spanning about 8 years now, I've discovered that it's a very effective way of spreading out your logarithm problems. And if you can use it well, oh my God, your work will be very, very neat. So this is what we're going to use now, and we'll go into problem solving. So the first one is a number you're given, The next one tells you the conversion in logarithm you are to make. And then the third one will tell you necessary corrections, necessary calculations you need to do. Rules can be bent, rules can be broken, but as we use it, you get to understand how best you would work with this. Okay, so we're going to solve a problem now. 2.413 times 3.092. And we're going to use our logarithm table to handle that. The first and the earliest concept of logarithm, use of logarithm, came from a man called, I think, John Napier or something like that. His concept was to try to deal with multiplication by adding. If you remember your indices very well, if you multiply numbers, what are you doing to their index or their indices? You are adding them. If you divide numbers, what are you doing to their indices? You are subtracting them. Remember that we said that the logarithm of a number is the power. So if power refers to index and power refers to logarithm, it will mean that if I'm going to convert this to logarithm or to logs for short, what you are going to do, or what the outcome you're going to have, will be these values, and we end up doing what? Adding them together. Now that's one thing you need to remember. Another important thing you must take note of here is this. When we work with logarithm, with our logarithm tables, we are assuming that the base is base 10. Please let that lock in. Anytime we multiply numbers and we are working with them, their logarithm, we assume that the base is what? Base 10. So the use of logarithm table would mean that the log we are dealing with there is what? Base 10. Please take note of that. Alright, so how do we do this? We are just starting, so I would insist you try to, first of all, write the numbers out in their standard form. Just like when you want to ride your bicycle, some people would want to, a phobia of falling or things like that. You introduce what is called a treading wheel. It's something that gives you balance, and after a while you take it off. So this is like our treading wheel. But for some students, if you can walk without your treading wheel, go ahead. It's just me thinking you may have issues with it. But if you can walk well without using this one, go ahead. And in fact, by the time we've solved a number of examples here, I trust you should be able to walk without using this interface. Alright, so what's the standard form of this? This will be 2.413 times 10 raised to the power of 0. There is no movement here. This will be 3.092 times 10 raised to the power of what? 0. There's no movement. Now, in writing the log, you will write this 0. This 0 here is what you will put here. This 0 is what you're going to put here. And then you will go to your logarithm table and look for 24, first two digits. So let's have this by way of, if I have 2.413, in your mind eye, you must assume all of these digits without the decimal. The first two digits is where you should check the logarithm. Under this, and this will take care of the difference. So if I'm to check for this in my logarithm table, I'll look for, see, remember I said that you must imagine, you don't see this point. You're not seeing that. You will see 24 under what? 1. You get the value out, so let's check that 24 under 1. So I go to my logarithm table. If you look at your logarithm table, you will see a column written X on the extreme left hand corner. On that column, you discover the highest number, the lowest number you have there is 10. So you look for where you have 24 there, And you're going to see just after x, you're going to see 0, 1, 2, 3. So that's where you are checking. That one is called the under. And after that, you see a colon written what? Difference or differences. So you go to your table, look for 24 under 1. If you have done that, you're going to get 3820. 3820. Difference 3. And that will be what? 5. So you check for 24 under 1, difference 3. So you get this out. Please get somewhere rough to do this. Like I said again, some students are smart. They can actually work this up on their brain before producing the answer. But I will advise you, while starting, write it out so you don't make a mistake. The difference is always added to the last digit. If it's a single digit, write to the last digit you just read out. If it is a double digit, then use the last 2 digits in the addition. So with that, you're going to get 3825. So you come to this point and write what? 3825. The next thing you want to do is to check for the next number. The next one is what? 30. Under 9, difference of what? 2. So you go to your table, you look for 30, where you have x, under 9. Under 9, you use your hand, you trace through, and if you've done the right thing, you should get something like 4900. 30 under 9, difference of what? 2. And the difference of 2 there is what? 3. And if you add that up, you're going to get 4903. I'll do another video. I'm making a promise to you that I'll do another video where I would place the book so you can see. I know for some of us we are struggling to what are we saying? I've not seen logarithm table before, whatever. I'll do a complementary video to that so that you can follow up on what we are doing. Alright. So with that said, you're going to get 4903. Now, because you are multiplying these numbers, the rule says that you are actually what? Adding their logs. So you add it up. Normal addition. Normal primary school addition. This will be what? 8. This will be 2. This will be 7, carry of 1. This will be 8. And this will be 0.8728. So that is the... When you multiply these two numbers, what you get in logarithm will be this. But that's not where it ends. We now need to look for the what? The number. If you heard me carefully when I was talking initially, I said something very interesting. That the number is the antilog. Another name for number is what? Antilog. So when they tell you, when you're giving a logarithm and you're told to look for the number or the antilog, they mean the same thing. So what we have is 0.8728. Now, in writing this, the antilog is always a number in its unit decimal form times 10 raised to the power of what? Look at these digits. What is written here? 0. That is the power to which that number is raised. This digit you've gotten at the end tells you what this 10 is raised to. Now, the answer here must be expressed as a unit decimal. What do you have here? 0.8728. So you will then go to your antilog table. So let's go to our antilog table now. You go to your antilog table. Antilog table in your New General Mathematics is found on page 252. So, you will look for, if you check again, the highest number you have there is what? 0, 0. Are you seeing it? Are you seeing 0.00? Are you seeing that? Good. So, when we solve other problems, you will get to understand. Look at this. This is 0 points. So, what they are saying is that, looking for the antilog now, what you're going to have will be something like this. Oh, my screen can take that. Okay, let's take it a little upwards. 0.8728. 8728. This point will be what you will check under difference. Check under difference. So you will check 87 under 2. So 87 under 2 will be what? Don't worry, you can chorus that out because it's we need. Okay. 7447. Then difference of 8 is what? Difference of 8 is 14. Is 14. Okay, so you add 14 to that, and your answer becomes 7461. I'm right to that. Now, when you are writing the anti-log, you're going to write 7.461. I know it's quite, it may not really sink in well, but with time you begin to see the reality. Look at this. Look at this one. Look at this expression here. The logarithm here will be what? If I'm to look for the logarithm of this, it will be 4.67 under 0, and I'll get this. If I'm to look for the anti-log, what I'm doing is that this must be in its standard form, the unit decimal form times the number of decimal places I have counted. So what would this be? There's no movement, is that not? So my final answer becomes 7.461. Now use your calculator and punch and see if you're going to get the same answer. Beautiful. It's a technique that is new. I have not really seen this technique being used by teachers, but I have developed this model, and once you get it, it may look hazy, but once you get it, you'll be running. It doesn't really need you to really think of. Just look at it. Okay, at this point do this, like programming. At this point do this. At this point do this. At this point, just know what you need to do per time, and you're through with the problem. So let's take another one and see what happens. Okay, you notice that when we solved question 1, I didn't use this column. Yes, because there was no need for it. But I've discovered that to really solve problems in logarithm, you must have this column. These are just simple questions trying to help you build your momentum and give you a foundation or a base to work with. But when we go into more demanding problems, you discover that we cannot help but use this column. And this is where we will need to do a lot of work. Okay, so we go to question 2 on the board. We'll be using our aid because we're trying to use a technique. So the first thing is to write this out in standard form. This will be 9.124. How many steps did I move to make that? I check where the decimal point is and I move 1, 2. Is that not? So that will be times 10 raised to the power of what? 2. Now look at this, 53.55. This will be what? 5.355 times. Look at where my decimal point is starting from. I'm going to move 1 step in. And what I will have will be what? 10 raised to the power of what? 1. Is that clear? Now, in writing my logarithm, I'll pay attention to these numbers I've got here. This will be 2 points, and this will be 1 point. I seen that. This will be 2 points, and this will be what? 1 point. Now, I have not said something before now, but taking this example, I'm going to mention this. The log of a number has 2 parts. There's a part we call the integer part, and there's a part we call the decimal part. So let's have that as an introduction. If we have a number, for instance, like let's use the example we had 0.3825, which is what we've just done. This is a log. This part is what we call the integer part. This part is what we call the decimal part. This part is also what we call the mantissa. This part is what we call the characteristic. I'm not asking you to keep that, try to understand. No, don't worry. Some of these things you will understand them as we go on. But just know that for a number, a number like this, the logarithm, the log like this, there's always an integer part and there's always a decimal part. Pay very close attention to this information, because sometime later, when I introduce something called bar notation, you will understand this very well. But for now, just keep it at that, just for you to know and keep your curiosity alive. Alright, so let's come back to our problem. So, remember I said that you don't bother, once you've gotten this part, you should not be seeing the decimal point anymore. You shouldn't bother yourself whether you're seeing the decimal point or not. What you need to do now is to go to your logarithm table on page 251 of your New General Mathematics, and then check your logarithm, look for 91 under 2 difference 4. So by way of helping you, it is 91. It is 91, check under difference. So check under difference. Okay, maybe I should write that a little bolder so that some of us who are at home might want to. So this is check under difference. So check under difference. Okay, so if you've done that, let me. Okay, so that will be 91 under 2, and that will be 9600. 9600. What am I right on that? Difference 91 under 2 difference 4. That will be 2. So that will be 9602. You have to be very careful when you're doing this. As a standard practice for me, I really don't bother myself so much about this. This is pure arithmetic, so I would expect that you don't make an error here. But you need to be very careful when handling this aspect. We go to the next one that says 53 under 5, difference what? 5. So it is check under 5, difference 5. So check 53. Beautiful. So that's what? 7 to. Okay, difference is 3, is that not? So that will be 7 to 8, 8. Alright, so that takes care of that. So that will be 7 to 8, 8. Beautiful. I usually don't like interjections, but in a topic like this, we need to have interjections from time to time so that it makes it real, very real to us. So thank you, students, for that. Now, the next thing we want to do is to subtract. Is to do what? To do your subtraction. Okay, we'll do a little correction to this. This will be 4, and this will be 4. Okay, you have to be very careful here. Precision is of utmost importance here. So we are subtracting. We are what? Subtracting. So we do the subtraction. 2 minus 8, not possible. I can't take from here, so I'll need to take 1 from here, and this becomes 5, and this makes this 10. And I'll take 1 from here, this becomes 9, and I'll add that here. So this will become 4, and that will be 1, that will be 3, and that will be 2. 2 minus 1 is what? 1. So we have an interesting one here, 1.2314. So we go to our antilog now, which is the number. The antilog is the answer. The antilog is the answer we are looking for. It will be equal to what? Whatever it is times 10 raised to the power of what? 1. This part was what? That tells you the power to which 10 is raised. I see that. So when you finish doing this, you check for this. Now be 10 to the power of what? 1. Then you go to your anti-log table. This is what you use in your anti-log table. This is the part you use in your anti-log table. So you go there, you check for 23. Please don't make the mistake of checking in your logarithm table to give you a wrong answer. So go to your anti-log table and check for 23 under 1. I'm getting this. Please confirm for me. 1702
plus 2.
Difference 4. That's 2. So that will be 1704. So that will be 1.704. So though you read out 1704, technically what you should write should be what? 1.704, because that is the expression of the number in standard form. So this is what you're going to get. So what is now the final answer? The final answer will be equal to what? This step means move this one step forward. 17.04. So this is the final answer you're going to get. Okay, trust you had a nice time today with logarithm. It's a very, very interesting and yet big topic. But we'll try to keep the things very simple. And I know it's quite different from what you have been doing before now. No problem. There are other videos that will come up in the future, and when we watch them all together, we give a greater perspective to what we have done today. So for now, it is Mamo with Jarvis signing out and asking that you keep the Mamo experience alive. Thank you very much.